12th and penultimate neural network architecture session. My name is Joseph Gonzalez. I'll be coordinating this session and the session after that. They'll be back to back. We'll have 4 talks in each session. The first 2 will be 20 minutes and the second 2 will be 10. So our first speaker for this session is Jonathan Schwartz, who will be talking about progress and compress, a scalable framework for continuous learning. Thank you.
Thanks very much. Can everyone hear me? Great. So I've got the pleasure today to talk about continual learning, some work that we've been doing at DeepMind with a great number of great collaborators here. So let me just take a second to define the problem. So continual learning is really about the incremental accumulation of knowledge acquired through the sequential mastery of tasks. So just to show you roughly what this is about, so here you could imagine a robot doing all sorts of different tasks in a sequence, and we can basically define a few challenges for the problem. So the first one would be we would expect some sort of positive transfer. That is really, we have sort of seen similar problems in the past. In the robot example, this could be perception and grasping is shared among these tasks. So we would maybe expect better generalization or perhaps better data efficiency. So the next challenge could be scalability. We want to have a method that is that has no obvious limitation to its applicability to a large number of tasks. And finally, also, probably the challenge that has received the most attention is the catastrophic forgetting problem. So this is the problem where the tendency of a neural network that sort of performance on a previous task is abruptly lost as new data is incorporated. Okay, so really, well, what's missing in the research field so far? In my opinion, really, what's been happening is that there's been a lot of sort of interesting papers on the problem, but usually there's been an overemphasis on one of these challenges, and that sometimes led to actually direct sort of decreases in performance for one of these other challenges. So what I'm going to be introducing is a sort of computational framework that operates in different phases of learning, and that really allows us to take some of these existing algorithms and take advantage of their strengths while mitigating their weaknesses. Okay, so how does this work? So here's a little diagram of essentially a reinforcement learning problem. So we might have some neural network that is estimating a policy and a value function. So this is some sort of actor-critic algorithm. Continual learning is all about the sort of sequential learning of tasks. We're not in the domain anymore where we look at tasks in isolation. So we could just train a sort of separate neural network for each of these tasks that we see, in this case 2 tasks. And I'm going to be using these sort of green and blue colors to essentially denote parameters that are being updated as well, and parameters that are sort of frozen and kept unchanged. So tackling sort of the first problem of positive transfer, we could introduce some sort of lateral connections that might have their own parameters that might allow us to actually reuse some of those features. We could be continuing to do this for essentially every new task that we encounter, and this is essentially a strategy called progressive neural network. So that's been released about 2 years ago, and it has sort of some interesting properties. So just by construction, this is essentially immune to forgetting. So given the task label, we can sort of pick the right network, and then we will sort of regain the performance that we had at the end of training. It's conceptually simple, so it shouldn't be too hard to implement this in your sort of favorite neural network library. And despite its simplicity, though, there's been some quite impressive results on video games, as well as some transfer from simulation to real-world data and robotics. However, one of the problems with this method is that sort of scalability here isn't really addressed. In fact, since we initiate a new column, essentially neural network column for each problem, given the size of these neural networks that people train these days, very quickly inference is going to be computationally intractable. So we're going to sort of abandon this strategy to some extent. That brings me to our method. Essentially, the method is going to work in two phases that are called the progress and compress phase, and hence the paper title. So the progress phase looks very similar to the progressive net setup in the sense that we will have a sort of a neural network column we call a knowledge base, which is really going to represent the accumulation of knowledge over time. And we're also going to have an active column. So this looks very much like the progressive net framework. However, we're going to be reusing this active column. Essentially, after the task has finished in the sort of compress phase, we're going to make sure that skill is recovered in a knowledge base, and we can reinitialize this active column parameters. So this way, we maintain simplicity, avoid architecture growth, and actually reserve sufficient capacity to learn a new task. So upon convergence on a new task, we're now going to take care of the sort of compression phase. So what we're doing here is essentially knowledge distillation. So note the change of colors, right? While previously we were optimizing parameters in the active column, we're now optimizing parameters in a knowledge base. And what we're going to be using is a sort of knowledge distillation loss. So we're just going to try and match those two distributions. So this is actually a supervised learning objective, and reinforcement learning has the additional sort of advantage that the distillation loss does not depend on the scale of the reward scheme. The question you should be asking yourself, well, how does that actually sort of work in the catastrophic forgetting setting? Really, if we wouldn't take care of anything, we'd just be overwriting whatever was in the knowledge base before. And so this gives me the chance to actually emphasize the fact that this is supposed to be a framework that can be readily combined with some other sort of algorithms of continual learning. The particular choice we chose is elastic weight consolidation, or in short EWC, and I'll show in a second why this is a particularly attractive choice. But really, what we could be doing is many of other algorithms. So here's just a small list of papers that came out in the last 2 years, and it's an active research area, so new papers are introduced fairly frequently. Actually, I think the next talk is going to be about continual learning as well, so looking forward to hearing about that. The new compress phase is going to look something like this. So we essentially have the same kind of knowledge distillation term, but we will also have another term that is essentially a regularizer. And the first term will say, distill knowledge from the active column. The second term will say, stay close to previous parameters. So this is how we will avoid the forgetting problem. So EWC essentially is an algorithm that works as follows. So say we have optimized our neural network on task A. So we found some optimal parameters theta star A. And what we're now trying to formulate is an objective that eventually defines a trajectory during optimization that leads us to a region in essentially parameter space where we have low error for both tasks. So we can formulate this essentially by writing down simply the sort of multitask likelihood. And in EWC, we will simply use Laplace's approximation, or in statistics maybe known as the delta method, for the likelihood terms. So upon conversion on this particular task, we will say that we'll approximate the likelihood with a normal distribution centered at the optimal parameters and the inverse of the Fisher information matrix. And in fact, so since this is a high-dimensional space, we're just going to use the diagonal. So this gives us a sort of new task to optimize, new loss to optimize for the next task, which is really essentially just a negative log likelihood times this regularization term. I want you to pay a particular attention to the summation here. So what this is really saying is that for task I, we have I minus 1 theta stars and I minus 1 sort of diagonal fissures. So this really means that we're storing twice the number of model parameters for each previous tasks. So this really seems to be in conflict with the scalability challenge, essentially, for continual learning. So fortunately, there's a way out here. In online EWC, which is sort of very close to the original EWC, as pointed out in this kind of blog post turned archive paper, we can apply Laplace approximation to the entire posterior. So what this kind of decomposition is saying is that really what we're going to be considering is the likelihood for the current task times the approximate posterior of all the tasks that we've seen so far. And so if we now use Laplace's approximation sequentially, we end up with a loss that looks more like this. So this is fairly similar, but note that the summation here really is at so we're actually sort of having a running sum of fissures and only one set of sort of theta stars. So we're going to recenter at the latest optimal parameters. And we can essentially just keep this running sum of fissures. So we have a constant number of parameters. So that is, we have twice the number of model parameters just to store these optimal parameters and the fissure. So to summarize our model, we have a progress phase that is really about sort of forward transfer and learning a new model. And we have a compress phase that is all about accumulating knowledge and avoiding the catastrophic forgetting problem. And just by decomposing learning in these two phases, we have really a method that is much more scalable. We don't require storing any old data, or essentially we won't also require any task labels since we don't have any model-specific parameters. So this is essentially how we learn a particular task, and for the next task we see, we essentially iterate between these two phases, giving us the progress and compress framework. So how well does this actually work in practice? What I'm going to be doing is I'm going to show you how well we do tackling some of these subproblems, and then I'll show you essentially how the method works in combination. So to assess catastrophic forgetting, we're going to look at omniclot. So this is this data set of 50 different alphabets, and we're just going to treat this as a sort of optical character recognition problem of 50 different alphabets. So the plot that I'm going to be showing here is all about forgetting. So we're going to be starting off with a performance that is essentially 100% on the first task that we learn. We're going to see how this performance sort of decreases over time. And so if we use a method like fine-tuning, so this is essentially just using the sort of supervised learning loss without any regularizer, we'll, after about 5 to 10 tasks, we essentially lose performance on this particular problem, and that is essentially what catastrophic forgetting means. So if we use the EWC variance, we actually manage to retain about 70% of the performance even after 50 tasks. Here's another baseline. That is another sort of algorithm that protects against forgetting. Learning without forgetting does actually fairly well in the beginning, but unfortunately for long sequences of tasks, this doesn't seem to be a suitable method. When we apply online EWC in the progress and compress framework, so this is going to be abbreviated PNC in all of the plots, we actually also manage to, retain some of this performance. So looking now at some sort of positive transfer experiments, we're going to be looking at sequences of Atari tasks. So here's a table with some models, and essentially each of the entries in the table is going to show us the increase or decrease in performance after having trained on a varying number of previous tasks, measured against just learning this task from scratch. So using just EWC without this sort of progress and compress phase, we actually have quite catastrophic influence on the positive transfer task. And this is really what I meant by saying that some of the continual learning algorithms trade one challenge for the other. So we really, after just learning a single task, in order to not forget, we sacrifice the ability to even get close to the previous performance. If we use fine-tuning, of course, we have this problem of not being able to remember, but we get some positive transfer in this particular case, so up to about 25% improvement in generalization. Essentially in a reward and reinforcement learning setting. For progress and compress, if we sort of keep reinitializing the active column, we reach about 25 to 30% pretty constantly. Looking at the entire method, so this is going to be an experiment again on 6 Atari sequences. The difference is now that we're going to allow revisits to the same task. So each of these vertical bars essentially is a revisit to the same problem, so we're just going to cycle through the task multiple times. So here's how the sort of EWC methods would do. Essentially what we see is that we don't lose performance, so that's good. We don't have this catastrophic forgetting problem, but also even though we get to see new data from the same task, we actually don't really improve over time. And so for our method here, this was a particularly nice example. We actually do significantly better. So the full results for that experiment are here. So this is basically learned top to bottom, left to right, and in some cases here really we manage to quite outperform the other methods. In cases where we don't, we perform quite similar. Okay, so it's showing you the entire performance also in omniclot. We can essentially take progressive neural nets as they don't suffer from forgetting, as well as a single model trained per task as the upper bound on performance. And notice here the number of parameters. So while progressive net here is an incredible large number of parameters, so those are 50 tasks, we are sort of fairly modest and also constant. So looking at sort of 5 passes over these 50 alphabets, actually, we also see that our method, outperforms some of the simpler baselines. Okay, so in conclusion, we have a new framework that essentially combines some of those challenges. We have positive transfer and diverse tasks, and I encourage you to read the paper because I could only choose a small subset of many of the experiments that we've run. So this is hopefully readily combined with other methods guarding against forgetting, as long as they're applicable in the single neural network setting. And we won't need any architecture growth or data storage. If you're interested in this, there's a poster today, this evening, which is poster 168. There we can talk about everything in more detail. Finally, I'd like to thank my collaborators that have been incredibly useful throughout the project. And I think with that slide, I would be happy to take questions.
have time for a few quick questions? Yeah, if you go to the mic, that'd be great.
Thanks for the great talk. You show experiments on a relatively large number of tasks, but eventually one might expect that you might run out of capacity of the network if you just keep increasing tasks, right? So can you think of a way this can be extended to when you have an increasing number of tasks or so?
Okay, so the question really is about scalability again, and it's about, if I understood it correctly, it's about the capacity case here of essentially the compress phase. So I think that some of the other continual learning methods sort of don't make as strong assumptions on scalability as I do. So one way in which you can actually sort of avoid forgetting is by storing some sort of trajectories from all tasks. So this is quite useful. I think also that maybe we can sort of improve on the scalability side if we encourage additional sparsity in the compression phase. So maybe this is a way of scaling to an even larger number of tasks.
Hi, great talk. How do you think it would work? How important is EWC in the consolidation phase? Like, can you avoid doing that, or can you? How important it is to use the EWC regularizer in the consolidation phase with respect to just leaving the knowledge distillation framework loss to this to work?
Okay, so this question is all about the importance of EWC. So essentially what happens if you don't use any protection against forgetting is that you get essentially this problem, right? So if you don't have any sort of regularization term that discourages forgetting, then you essentially have the same problem as before, such that your sort of performance on a previous task is going to deteriorate very quickly. Maybe there's a few ways of getting around this, for instance, by pruning a neural network after we've done this particular kind of compression phase. But this is an experiment I didn't have a chance to perform.
Just a quick question. How important do you think it is to have task segmentation? So did you do any experiments where basically you don't know when tasks end and begin, but you're just continuously doing this?
Yeah, I think that's a great question. So I mentioned essentially as some of the challenges for continual learning. In this case, we really focus on different kinds of challenges. I think that maybe the question that you're talking to is about sort of a gradual drift between tasks. That is, there's no clear task boundary. I think that, okay, so in our particular framework, later on when we apply the knowledge base and we assume the same action space, we don't actually need the task label. I think when it comes to gradual drifts between tasks, this is quite challenging because this framework still, essentially during training especially, we essentially assume that we know the task boundaries, which might not be easy to determine in your case. So I think this is a great question, maybe a good avenue for future research.
Hello. My question is more related actually to the EWC, but perhaps you experimented it while dealing with your framework. Have you checked the sensitivity basically of the results with respect to the approximation of the fissure that is being used instead of diagonal, some other approximation, etc.?
Okay, that's a great question as well. So let me see if I have a reference. We actually stick with the sort of diagonal approximation. I might not have a reference here, but recently there's a paper that came out of a group at University College London where they essentially use a better approximation to the fissure, and that actually helped a lot. So yes, if you do use a better approximation, you should expect improvements in performance.
All right, let's thank our speaker.
Thank you.
All right, so lest we not forget, the next speaker is next speaker is Joe and Sarah, who will talk about overcoming catastrophic forgetting with hard attention to the task.
Hi everyone, thanks for coming to this talk. And I am Joan Serra, I'm a research scientist at Telefónica in Barcelona, and this is joint work with Didac, Marius, and Alexandros. And guess what? This work is about catastrophic forgetting. Let me, even though you may know what it is, let me summarize in plain words and easily what it happens with this problem, and maybe give you a different perspective too. So essentially put it, catastrophic forgetting corresponds to the fact that when you learn a second task, you don't know how to perform the first task anymore, right? If we put it in simple terms, so here let's consider a binary problem here, distinguishing between photos of cats and dogs. And let's consider just two simple features and a simple linear classifier here. So you train on this task, you learn your boundaries, you know how to classify this with great success, and then you move to the next task. So now the task is distinguishing between cars and houses. So again, you train your fancy classifier here. And by the way, catastrophic forgetting is not a problem of neural networks. It's a general problem in machine learning. So as you see here, it's just a linear classifier. So you train your classifier here in this task. You again perform awesome. But then when you look at what happens when distinguishing the boundaries for the first task, basically these don't match. And you can say you have forgotten everything, right? So of course, this problem is important if we want to build more general artificial intelligence systems, and especially if we want them to learn sequentially. I mean, for instance, I think it's quite unrealistic to suppose that a robot will have all possible information about the world, all possible tasks at the same time to train concurrently. And even if this information was available, doing this multitask learning concurrently when the number of tasks is so big and the number of examples is so big, I think it's totally unattainable. So this is not a new problem. There is a lot of work done with that. So in fact, since the 90s, it has been tackled, but still not solved. And then some strategies imply the use of some memory modules, what is called a rehearsal strategy. So basically, you replay all past events in order to remember the past. Then you have another strategy, which is not playing exactly the same events, but maybe with a GAN, you generate things that look like previous tasks, and then you replay them. And then you have a bunch of approaches which are devoted to reduce representation overlap, and my colleague here in the previous talk has done a very good summary on that. Hopefully now you know about elastic weight consolidation and progressive neural networks and all these methods. So our method is one of this type. It tries to reduce representation overlap, and it combines protection of certain parts of the networks and reusing existing parts of the networks. So we name our method putting hard attention to the task, and I will start by giving you a bit of motivation of our method. So here, let's consider this simple data set. So it has these images, and I tell you now that the first task is distinguishing between birds and dogs, so we can easily do it. But then let's consider the exactly same data set, and now let's switch the task. Now the task is distinguishing between brown and black animals. So here, clearly, the data set is exactly the same, but the task has changed. And what happens here? The task ID is different. So here, it came our idea that we shall exploit task ID in order to do sequential learning. So in this case, our idea is to take the task ID as form an embedding of this task ID, and then use these task ID embeddings to condition the output of every layer of our network. For instance, in the first task, we may learn actually that some neurons are very important, and therefore we can freeze them for the next task. Then in the subsequent task, we can still reuse these neurons that we learned in the previous task, but now we learn new ones that are more focused on the new task. Then we can freeze all of them for the next task and continue to do that, okay? So let's go a bit more into detail. So this is schematics of our approach. So here on this side, you have the main network. So these are the layers. And the only thing we do is that we introduce this multiplicative term, and we multiply with this hard attention vector, which is just the result of scaling the embeddings by this parameter S, and then going everything through a sigmoid function, and then we get our attention vectors. They are between 0 and 1, and therefore they activate or deactivate every neuron at a time. So the objective here is to condition the output of every layer's units, and with the possibility of totally activating them if it's a 1, or totally deactivating them if it's a 0, but also with the possibility of weighting a little bit their contribution, so values in between 0 and 1. And then we have this other part of the network that at backpropagation, in order to prevent forgetting, we want to freeze the weights that were important for previous tasks. And to do that, we accumulate these attention vectors over tasks with this max operation. So basically, if they were very important, they were a 1, so they are going to be always a 1. They are going to be always frozen, because then we multiply by 1 minus this when at the backpropagation stage. So it's this formula here. And then you may wonder, okay, but if there is a sigmoid and you ideally want some binary operators, how do you learn them? Because it doesn't have a gradient. So what we use here is an annealing scheme, an epoch-based annealing scheme, and we set this parameter Smax between some values that go between some small quantity, not exactly 0, and some large quantity. So think if it's 1 S, this corresponds to the normal behavior of the sigmoid. If S grows a lot, it's more like a step function, and we get this binary behavior. So here the objective is to let the gradient flow through the hard attention gate when the attention gate is not fully closed, is not fully binary. This introduces some problems with the gradients, but so in the paper we first identify them, and later we propose an analytic form to compensate for this lack of gradient in the embeddings. I don't put the details here. You can check the paper for the exact formula and for an intuitive explanation of it. So finally, another important thing that we need to take into account is that we don't want to consume all the capacity of the network in the first task. Therefore, we introduce this regularization term here on the top, weighted by this parameter C. So basically what we do is that it's an L1, it's a weight, you can think of it as a weighted L1 norm. So basically we promote sparsity, but not in the weights of the network, but on the output of every layer, so in the output of every neuron. And we use both convolutional and fully connected layers. We use dropout, so this method is not specific of multi-layer perceptrons, but can also be extended. Right? So here, as I mentioned, the objective is to prevent dedicating all available units to a single task and promote compression. And the nice thing of this is that we compress at the same time we learn, thanks to this regularization term. So basically, at every iteration, we learn the task and learn how to compress or learn which attention to put at the task concurrently. So let me show you now some results, but first of all, I want to mention some words about our evaluation setup. As we argue in the paper, many of the evaluation setups for catastrophic forgetting are a bit biased or flawed. So here we consider 8 different image classification datasets, not the same dataset, and applying different and considering different classes one at a time. And we compare against an extensive baselines like the progressive neural networks or elastic weight consolidation that has been mentioned in the previous talk. We test both convolutional and multi-layer perceptron architectures. And in order to be able to compare against different tasks and task sequences, we need to do several runs. And accuracies cannot be compared directly. So we derive this simple normalized ratio, which is just, you can think of it as the amount of forgetting you get. So it goes between 0 and -1. So if it's -1, you forgot everything. If it's 0, you forgot nothing. So here are the results of our approach in this multi-data set task sequence. As we see, the proposed hard attention mechanism performs very well. Actually, we achieve between 45% and 75% reduction in forgetting with respect to the best baseline we could find. And yeah, we are not that far from this dashed line is the multitask classifier, simple plain multitask classifier learning concurrently. Besides this setting, we also test the classical settings like incremental learning tasks with CIFAR 10 and CIFAR 100. Here our results are also very encouraging. And then going back also to some other ways of evaluating these algorithms, we can compute accuracies after permuting the MNIST data set. So still here we again achieve very good results. Or we can compute accuracies splitting the MNIST data set between 5 tasks and 5 classes and 5 classes. So these results are very good. Another thing we want to look at is the amount, how do the hyperparameters affect the quality of the solutions. So remember we had two hyperparameters, this Smax parameter, which is the amount of closure of the sigmoid gate, and then the C parameter, which is the amount of compression we apply to our models, the amount of regularization we do. So essentially, Smax is not very important. We see that all curves are more or less at the same place, but then C plays a role. So if C is very weak or we actually don't compress, so in this case, because the capacity of the network is quite limited, it harms the approach. And besides results, I would like to show you a number of interesting capabilities that our model has. So one of these, for instance, is that thanks to these hard attention vectors, we can monitor the used capacity of the model. So here on the left, we can see that each color is one task, so we can see how we start using a lot of capacity of the network, but at every epoch, we start compressing the knowledge and learning again. So you see that the capacity gets reduced up to some point that it converges to some solution. Then for the next task, we have a peak again because we again use more capacity from the network and compress again, and we do so and so. And we see that in the end, we still have some capacity left after the 8th task in this case. Also, if we split these attention vectors between layers, we know which layers are more used and which are not. So in this case, we see, for instance, that after the 8th task, the first convolutional layer is totally full, and it's on after actually the 5th task, the first convolutional layer. Let me show you. Here is totally full, so the other tasks are just reusing the filters here. So we could even use this knowledge to guide the design of the algorithm. So like, okay, now the first layer is full, let's devote more filters to the first layer and use less fully connected neurons at the last layer, for instance, or something like that. Another interesting thing we can measure with these hard attention vectors is the amount of knowledge we reuse from previous tasks. So here we wanted to see results like, for Street View house numbers, we reuse a lot of knowledge from MNIST, for instance, but that's not the case. What happens is that the more capacity is used from the network, the more forced it is to reuse previous knowledge from the past, and basically that's the behavior we observe here. So in the 8th task, it's reusing a lot of information, but then at the beginning, it's not motivated to reuse that information. And finally, and very interestingly, as you might have guessed, we can use also these hard attention vectors to do compression of the network. So basically, thanks to this parameter C, we can tune it to favor compression. And here, I'm only considering a single task for demonstrating it, but here in this plot, every dot is an epoch result. So you see that as the accuracy increases, again, we are compressing the network. And we actually reach some good numbers for compression, and we didn't look much into the state of the art about compressing neural networks, but I've learned here in this conference that this could be actually something. I mean, I have not seen much better results in some papers. So finally, to conclude, let me summarize. So this mechanism, hard attention to the task, first of all, and that was our main objective, protects the information from previous tasks while learning new tasks and being able to reuse this information from previous tasks in new tasks. Interestingly, it only adds a tiny fraction of capacity to the base network because it only focuses on the outputs of the neurons, not on the weights. And also, this method is trained together with the base network, and in terms of time, it has minimal overhead. In the appendix, we have some results regarding that. And we don't use any evolutionary strategy or any fancy training method. We use just standard plain SGD. And it yields to effective cuts in the forgetting ratios between 45% and 80%, depending on the setting you consider. And it has only two hyperparameters, which are very intuitive. One is the amount of compression you apply to the network, that's C. The other is Smax, which is the amount of retention of past knowledge that you want to apply. And besides all this, it presents a lot of interesting capabilities, like these monitoring capabilities, the compression capabilities I've mentioned. If we tune Smax to be a little bit smaller, allowing a little bit of forgetting, it could be useful also for online learning scenarios or concept drift problems. And this concludes my talk.
So we have time for a few quick questions. While people are getting set up, I have a quick question. Is it possible you think that I could then use the setup you have to infer the task ID? Could I work backwards if I had a few examples?
Like it is now, maybe not. Because the task ID is an essential input. So basically, it decides which attention vector to apply.
You couldn't optimize over that dimension.
You mean the task ID?
Yeah.
Maybe, yeah.
Well, yeah, it does work if you use an hypernetwork for sure. But did you use batch normalization in your AlexNet? And in case, how would you handle the running means and variance of batch norm with changing datasets?
Yeah. Batch norm is because of this running means, it's the only place where we are not sure whether we could apply this method. But one simple option would be to just ignore it and assume that it's, the first thing I would try is ignoring it. We have not tried.
It doesn't work if you ignore it.
Okay. You tried? Whoa.
All right, if there are no more questions, let's thank our speaker one more time. All right, so our next speaker is Sensren Mukdalai, who will be talking about rapid adaptation with conditionally shifted neurons.
All right, hi everyone. Good to see you. So this is work towards developing neural nets that can predict its own connectivity for one-shot rapid adaptation to a new task. So in this work, we introduce a neuron level adaptation, which we call conditionally shifted neurons. We also introduce a new, less expensive conditioning information inspired by the idea of direct feedback alignments as an alternative to error gradient. So conditionally shifted neurons are a simple way to adapt neurons for a new task context, and it's applicable to various different neural network architectures. So in machine learning, we have IID assumption, which simplifies things as. Also, it gives us hope that our model can generalize in the future for, on the test data. However, it may not be true in real world. Traditionally, machine learning models are trained through one giant optimization path until training ceases. The model is then deployed for a test, and the model parameters are frozen until we retrain again. This setup scales poorly. The models built in this setup requires a lot of single task data to reach a good performance, also prone to issues related to distributional shifts. This setup also does not naturally support transfer learning or learning across multiple tasks. On the other hand, humans are very good at one-shot rapid adaptation. Question here is, can we teach our machine learning models human-like rapid adaptation? So we would like our neural networks to be able to predict its own connectivity on the fly. So in a new setup, the model sees a distribution of tasks. And for each task, model predicts its own adaptation first, and then using the predicted adaptation, model makes prediction for the final task. Now, this setup supports learning across multiple tasks and knowledge transfer across tasks naturally. So we introduced conditionally shifted neurons to implement the rapid adaptation in artificial neural networks. So neural networks with conditionally shifted neurons predict task-specific shift beta to its activation. So conditionally shifted neurons take the following form. We have a standard neural network activation on the left side, and the task-specific shifts on the right side of this equation. So the beta shift here is learned based on conditioning information that we extract from the model. So conditioning information is a type of feature that describes the model or neurons in a context of new task. For an example of conditioning information is error gradient. We also introduced like a new conditioning information called direct feedback, inspired by the feedback alignments in training neural networks. So direct feedback information is simply the derivative of activation scaled by the derivative of the loss. So for each neuron, it is C-dimensional vector with a C number of classes. So unlike previous approaches that adopt weights of neural networks by using either optimizer or using gradient-based fast weights, conditionally shifted neurons can be incorporated into different neural network architectures. For example, in ResNet, we augment the residual neurons with conditional shift. In LSTM, we augment the activation of the memory cell with conditional shift. In this case, the conditioning information is extracted at the memory cell. So we modify meta-networks architecture to learn the conditioning information, conditional shifts beta. So the model operates in two paths. In the description path, the conditioning information is extracted and transferred into shifts by using the task description or one-shot examples. In case of one-shot learning, the shifts are then recorded into a key value memory where key is embedding of input example. And in the prediction path, we obtain the embedding of the input example, and then using a similarity-based attention mechanism, we generate the shifts beta. The model is then shifted, and the task prediction is made. The whole model is trained in end-to-end fashion, optimizing the parameters of embedding function, the value function, and the base learner. So we evaluated our models on one-shot benchmarks in both vision and language domain. For example, on a mini-ImageNet benchmark, ResNet network with conditionally shifted neurons improved the previous result by 1.16 and 3 percentage for one-shot and five-shot tasks. On one-shot language modeling benchmark, our two-layer LSTM with conditionally shifted neurons improved the result of simple matching network by 11, 16, and 19 percentage for 1, 2, and 3-shot tasks. So in terms of speed, our model is about 100 times faster than the meta-networks, which implements weight adaptation with gradient-based fast weights. So I guess this concludes my today's talk. And I invite you to visit our poster, number 33, for more about our work and meta learning. Thank you.
Are there any questions? I have a quick question. So both you and the previous talk dealt with embeddings. Was there any need to encourage diversity in those embeddings? And did you see diversity in those embeddings after trying multiple tasks?
So diversity in terms of representation, or okay, so we did not look at that, like in terms of the representation diversity, but we did see that the embedding representations basically really varies across tasks. Initially we thought that the embedding representation that we learn is kind of clustering, but it's not apparently. It changes depending on the tasks that we are solving, for example. Yep.
All right, if there are no other questions, let's sing our speaker one more time. Thank you. All right, so the final speaker for this session is Yoon-Hon Lee, and he'll be talking about gradient-based meta-learning with learned layer-wise metric and subspace.
Thanks. Hi, my name is Yoon-Ho Lee, and this is joint work with my advisor, Seung-Jin Choi. We're both at PostSec, which is in South Korea. So this work is concerned with meta-learning, where we fix the learning algorithm to gradient descent. So what additional information can we give a network if we know we're going to use gradient descent? And kind of the easiest thing you can do is MAML, which learns initial parameters. So this is how that works. This is gradient descent. So yeah, you know what that is. We're going to denote task-specific things in green and things that are shared across all tasks in purple. So if you gave me two different tasks, if I was doing MAML, I would start from the same parameters called theta meta, and I would arrive at two different parameters called theta t. And how you train MAML, how you meta-train MAML, is that you backpropagate through this gradient update step back to theta meta. So in equation 1, we have the dependence of theta t on theta meta, and you just backpropagate through that to update theta meta so that performance after one gradient step is better. So our motivation here was that gradient descent is good, but it's kind of not what we do as humans. So if we're adapting to a new task where we have some experience in, we kind of figure out what we know and figure out what we don't know. We leave what we know and we only learn on what we don't know. That's kind of the intuitive way that came to me. So ideally what we'd like is for task-specific learning to be able to occur while only altering a small portion of the information that you've meta-learned. So to do that, basically we need two things. We need one, some way to restrict learning to a subspace of all the possibilities that gradient descent could go to. And two, if we call that a subspace, we want to know how to learn the subspace and encode it into a network. So that is what we do. We propose a neural network architecture called MTNets, which do exactly that. An MTNet is composed of cells as opposed to layers. And a cell is two consecutive linear layers with no nonlinearity. And what we do is, in that cell, we call the first layer W and the second T, and we only learn W during task-specific learning. And furthermore, we learn which weights of W we're going to learn. So you can see here there are 3 different tasks, and only the weights that are designated to learn, the dotted lines, have changed. So in equation form, it is, we're learning metaparameters, which is for each layer, the parameters of W, of T, and of the logits that govern which of W we're going to learn. And we learn by, note that all the purple stuff is shared. Using the logits, we sample a binary matrix which has the same dimensions as W, and then we element-wise multiply that with the gradient with respect to W. So if M, capital M had a 1, we're doing gradient descent there, and if it has a 0, we're not. And that way we obtain the task-specific parameters WTI, which is in green. And then we use the exact same trick as in mammal. We backpropagate the loss after updates back to the meta parameters. So we provide analysis of this in our paper. Basically, if you do this, you have sufficient capacity to restrict your learning to any subspace of any cell's activation space. And furthermore, the MTNet update is equivalent to doing gradient descent with respect to any metric that you can specify beforehand. We give a constructive proof, which is fairly simple. For experiments, we first compare with mammal. So mammal has inner loop step size hyperparameter, basically the learning rate of the inside gradient descent. And if you change that from the optimal value, the performance explodes. But TNets and MTNets don't do that because of what I mentioned before, where T can encode a metric. So therefore, it kind of has the effect of changing the effective step size. So if you gave it too small of an alpha, it would increase alpha and vice versa. In a different experiment, I'm not sure if you can see that, but we trained 3 separate MTNets on tasks of differing complexity. So we're doing fuse-out regressions to polynomials of order 0, 1, and 2. And clearly, polynomials of order 2 have more to learn. And if you, after meta-training, if you look at the M and how many of the elements of M is designated to 1, the MTNets choose to update more parameters for the more complicated tasks, which is in line with the intuition that we started with. And finally, we evaluated on mini ImageNet 5-way one-shot classification and got slightly better performance than all existing models at the time of submission. So in conclusion, we propose a new neural network architecture called MTNets that work well on fuse-out learning. They learn layer-wise a subspace with a metric, and because of the T component, they're robust to step size. And if you inspect the M after meta-training, it had some correlation with the complexity of the meta-test in an experiment. In future work, we would like to address this, which is, so you can view MTNets as a case study in a different way of thinking about optimizers. So the traditional way is you do backprop to get gradients and push those gradients through some learned or not learned function, and that's your update. And here what we did is we just directly applied gradients to the parameters, but there was something else inside the network that we weren't learning at the time that affected the loss surface, that kind of acted as an optimizer, like changing learning rates. So what we would like to investigate is how far can we take this idea of basically pulling back the optimizer into the network. And I think this fits into a larger line of research where people have been claiming that things like ResNet or batch norm, or earlier in this conference, there was a paper on over-parameterized neural network, like linear networks that had some effect on optimization. So I don't really have answers to this, and I would love to hear your thoughts at our poster later tonight. That's all I have, and thank you for being here.
Are there any questions? Yeah.
Hi. So can you, do you have an intuition if different tasks which are pretty close to each other, if we can measure the closeness between tasks, will have similar subspaces learned?
Well, in this work, we're sharing the subspace among all the tasks in our metaset. So I don't see how you could do that here, but I think somehow learning a distance metric between tasks is an interesting problem.
I have a quick question. So the cells look like a low rank embedding or low rank factorization of a single layer.
It's not low rank, it's full rank. So here you would have a 4 to 3 matrix, and you factorize that into a 4 to 3 by 3 to 3 matrix.
Okay.
Does that answer your question?
I guess if I take that whole cell and there are two linear operators and I multiply them together, I get a new linear operator.
Yes, yes.
Okay. So you're not constructing a low rank factorization of that new linear operator.
No, we just leave it at this.
Okay. Could I generalize this to a convolutional structure, or does it always need to be fully connected?
Oh, we do generalize it to a convolutional. Basically, you make T into a 1-by-1 convolution with the same number of input and output channels.
All right. If there are no more questions, let's thank our speaker one more time. All right, and that actually concludes the 12th neural network session. We will start the 13th neural network session in 5 minutes. and 13th session on neural network architectures. My name is Joseph Gonzalez, and I'll be moderating this session. As before, we have two 20-minute talks in the beginning, followed by two 10-minute talks. Our first speaker is Ning Zhu, who's going to talk about WSNet, compact and efficient networks through weight sampling.
Okay, thank you for the introduction. Hi, everyone. My name is Ning Xu, and today I'm going to talk about WSNet, compact and efficient networks through weight sampling. So this is a joint work with my intern, Xiaojie Jing from National University of Singapore, my colleagues, Yinzhen Yang and Jianchao Yang, and collaborators, Nipocha Georgic, Jiaxi Feng, and Suixin Yan. So what makes good compact and efficient deep models? So first of all, we want to have a small model size, and we want the model to can be computed fast. At the same time, we want it to have a high accuracy. So our proposed WSNet is such a compact and efficient network design. When we apply WSNet to regular convolution networks, it can achieve smaller model and faster computation and achieve better or compatible accuracy as a baseline network. So in some of our experiments, we achieve 180 times smaller network and 18 times faster. So we have a couple of key observations on the conventional convolution networks. First, the convolution filters are mostly initialized and trained separately. And second, those convolution filters are highly redundant. And because of this high redundancy, there are not works in the past that have been used for model compression, such as model quantization, model pruning, low-rank decomposition, and etc. So our proposed WSNet is also utilizing this high redundancy of the convolutional filters. In our method, we are not, instead of generate the filters individually or separately, we actually generate from a compact learnable parameter set. As we can see here, we have a small parameter set phi, and all the individual filters, W1 through Wn, is actually generated or sampled from this parameter set phi through a mapping function f. And in this work, we will use deterministic weight sampling for the mapping function f. So here I'm going to show a simple example of weight sampling, and we are looking at a 1D convolution case with single channel. So for our condensed filter map, we have only have 7 weights. And we use shift sampling, so we can, from these 7 weights, we can generate 5 different 1x3 filters. And if those filters are generated independently, it will have 15 weights. So this is basic idea of weight sampling. So we are going to do weight sampling in both spatial dimension and channel dimension. And this figure on the bottom right shows how we do the spatial weight sampling in the spatial dimension. At the bottom is the condensed filter phi that we mentioned before. The horizontal direction is the spatial direction. The vertical direction is actually the channels. So in order to sample the weight for individual filters, we actually use a sampling stride S and then shift the filters from left to the right with the stride S to generate multiple filters. So as we can see, there for these two sampled filters, there are overlaps between each other. So if the sampling stride S is smaller, then the overlap will be higher, and then we will have more reduction in the parameters of the filter. So we can also, as we mentioned, we can also do the weight sampling in channel dimension. So here we have very simple channel dimension weight sampling. We just, for example, if the input channel is M, so we just use M over C channels for the condensed filter. And once we sampled it spatially, we just repeat it C times to reach, to match the input channel numbers. So this way we can reduce the parameter number again by C times. So combined with weight sampling in spatial dimension, we actually can reduce the parameters by a large number. And here is a combined overview of the weight sampling method. So at bottom is a condensed filter phi. And we first do the spatial sampling with the stride S to get multiple overlapped filters. And then we just repeat it multiple times to get the needed filters, same dimension as the baseline network. So as we can see, I mean, if we are just using the weight sampling and do the convolution with those sampled filters, the computation will be the same. In practice, actually, we try to find ways to speed up the computation. So the speed up can be done in both the spatial weight sampling and the channel weight sampling. So this slide will show how we can do the speed up for the convolution computation for the spatial weight sampling. Since we are not considering the channel sampling, so on the bottom of the figure we see the condensed filter phi. We will first repeat it multiple times to match the input channel numbers. On the left side of the y-axis, we have the input feature map. The horizontal direction is the input channel numbers, and the vertical direction is the number of the input. So when we're trying to compute the convolution between the filter K1 and the input F1, so what we need to do actually is to calculate the inner product of each horizontal vector in F1 with its corresponding vertical vector in the expanded condensed filter. So each of this inner product, we can represent it in the inner product matrix P as a dot. So if the length of the filter is L, then in order to compute this convolution, we need to calculate L inner products. And the convolution result will be the summation of this L inner product result. So this L number of inner product result can be seen in the inner product matrix P as a red line. And then when we try to calculate the convolution between filter K2 and the input feature F2, we need to compute all the inner products as represented by the blue line. So as we can see here, there are overlaps represented in green. That means because there are overlaps in the convolution filters, so when we calculate the convolutions, there are also overlaps, and we don't need to calculate as regular convolution neural networks. We can speed that up because we don't need to calculate again for those overlap areas. In addition, we can speed up the calculation of convolution using the concept of integral image. So after we calculate the inner product matrix P, we can compute an integral image I on top of it. The idea is that we can accumulate the values on the 45-degree line. This way, when we need to calculate the convolution, for example, convolution between the kernel K1 and feature map F1, we just need to find out 2 endpoints of the red segment and subtract them. The difference is the convolution result. That means after we calculate the integral image I, the calculation of convolution will be just lookup and then subtraction. Because we can do that, the convolution becomes an O1 operation. We can do a much dense weight sampling. We can sample more filters with a small stride to increase the capacity of the network. In addition, we can also sample more filters with different filter size. So from filter size from 1 by 1, 1 by 2, till 1 by the entire length of the condensed filter phi. However, computing the convolution using these dense sampled filters will not incur any additional parameters or additional computations, but we will have much more output channels than the baseline. And what we can do is that we can use 1 by 1 convolution to reduce the output channel to match the baseline network's output channel. And also we can use the channel pooling, try to reduce the number of channels. We can also speed up the computation for the weight sampling in channel dimension. So what we do before is to expand the condensed filter phi, repeat it several times, and do the inner product computation. So instead of doing that, we can actually separate the feature map into several columns and add them together. So we call it channel wrapping. So we can wrap that feature map so that the channel number will match the condensed filter's channel number, and then we can calculate the inner product matrix with the less number of channels. So if we repeat the filters for C times, then we can reduce the calculation by C times this way. And we also extend the WSNet. So what we did before is all on the 1D convolution. We also extended directly to 2D convolution. Extending WSNet on 2D convolution is quite simple. For channel sampling, it will be exact same. We just repeat the sampling in the channel dimension. For spatial sampling, we will just shift the patch sampling of the 2D patches in a 2D condensed filter. Like this, we can have overlapped patches in the 2D condensed filter so that we can reduce the parameter numbers of the filters. Now I'm talking about the experiments. We have done several experiments on audio classification. Here we show that the experimental results for a task of ESC50. ESC50 is a collection of 2,000 short environmental recordings comprising 50 classes of different sound. And we use a baseline network called SoundNet. The table here shows that the SoundNet contains 8 different convolution layers, and it also shows the filter size, number of filters, stride, number of parameters, and number of multi-adds for each convolution layer. This table shows the different configurations of WSNet compared with the baseline network. And first several columns shows the configuration, and the last 3 columns shows the accuracy, model size, and the multi-add numbers. As we can see at the last row, we actually achieved 180 times smaller model size compared to the baseline network, and the performance is only dropped like 0.2% from 66% to 65.8%. In another configuration, we can see that we can achieve 18 times speed up and 60 times smaller model size. and accuracy is dropped from 66% to 65.2%. So we have more results on audio classification. We can see in the paper and some supplemental materials. This figure shows that we compare the WSNet with the Linode baselines. So the Linode baseline is that we try to reduce the channel numbers, reduce the filter numbers in each convolution layer to match the parameter numbers in the WSNet. So from this figure, we can see that for all the different compression ratios, the WSNet shown in blue performs much better than the Linode baseline networks. We also compared WSNet with HashNet for image classification. So with the direct 2D extension of WSNet on two tasks, one is CIFAR10 and another one is MNIST. So we choose these two because HashNet is using these two tasks. And also we choose the same number of model size reduction, 16 times and 64 times, so that we can compare with HashNet directly. From the comparison, we can see that WSNet in both tasks performs better than HashNet. So here is the conclusion. So WSNet provides a novel design scheme for convolution neural networks to learn compact and efficient models. And it achieves comparable accuracy, but with much fewer parameters and less computation cost for convolution networks. For future work, we will explore better ways to apply WSNet on 2D inputs, and we also will explore more filter generation methods other than the structure sampling that we use right now. Okay, that's pretty much it. Thank you. And our poster is just number 6 tonight.
Are there any questions? I have a quick question. On one of your accuracy plots, your accuracy went up after you compressed the model and stayed above the baseline.
Yeah.
Do you have any thoughts to why compression improved accuracy?
We see a lot of cases that accuracy actually getting higher when we just compress a little bit. I think one of the reasons is that the generalization power is getting better, and also because when we are trying to use overlapped filters, actually there are some of the patterns in the overlap area we can actually utilize it. We visualize the filters in audio classification. We see there are some overlap areas that actually have similar patterns.
Those are for audio signals that,
Audio
so
signals.
could there have been a phase advantage? You're moving the filter over in time?
We didn't consider that. Yeah.
All right. Are there any other questions? All right, let's thank our speaker one more time. So our next speaker is Michael Shannon, who'll be talking about Strassen nets, deep learning with a multiplication budget.
Okay, thanks for the introduction. So yeah, in the last couple of years, we have seen some great advances in deep learning, but I think it's clear to everyone that these advances come at the cost of a very high computational complexity and therefore at the cost of a high energy consumption. And we have learned yesterday in the plenary talk that this trend is actually not really sustainable and that we're going to hit yeah, some limitations fairly soon in terms of compute if we don't make these architectures more efficient. Now, this is not known since yesterday, but has been known for a fairly long time, and people have come up with different methods to make these architectures more efficient, and yeah, some of them are listed here. So you can do architectural optimizations using factorizations of weight matrices and tensors. You can prune weights or even better filters. That was also mentioned in yesterday's plenary talk. And another very popular approach is reducing numerical precision of weights and activations. Now in this work, we took a slightly different approach. So all the methods I mentioned before, they reduce, multiply, and accumulate operations. So they reduce adds and multiplication at the same ratio. And in this work, we specifically target the multiplication operations. Now, why do we think this is a good idea? So first of all, this algorithm design principle of reducing the multiplications has led to many fast algorithms. Probably well known from introductory algorithms class is Strassen's matrix multiplication algorithm, and more recently and more related to deep neural networks is Vinograd filter-based convolution. And this reduces the number of multiplications by a factor of 2.25x and leads to a speed up of 2 to 3x on GPU, so which was pretty significant. Now there is some other work from the FPGA literature that shows that if you take a neural network that has weights, so ternary weights -1, 0, and 1, so these can be implemented using sums and differences, so with only very few multiplications. So these people observe that they get a higher throughput and they also reduce the energy consumption. Now, if you think about edge devices, microcontrollers, depending on the architecture, in some cases you can get multiplication take up to 32x more cycles than additions. So trading off a lot of multiplications against some additions may be beneficial. And then finally, if you think about custom chips, their multiplications usually take, or multipliers usually take more area and therefore consume more energy than additions. So this difference can also be quite significant depending on the precision you're aiming for. So yeah, for all of these reasons, we think it's worth studying multiplication reduction specifically. Now, yeah, so most of the arithmetic operations in deep neural networks, at least in vision, they can be cast as matrix multiplication, be it in or matrix vector multiplication, be it in fully connected layers or also in convolutions. And these matrix multiplications, in turn, they can be written as some product network, as shown here on the right. So these are arithmetic circuits. So these networks, these small networks, take the vectorized arguments of the product as an input and produce the vectorized result as an output. And they have this hidden layer of multipliers here, and they also have these edges here, here denoted by these matrices WA, WB, and WC. And these edge weights here, they are ternary, so they are either -1, 0, in which case we could remove them, or +1. So basically, such a network can be used as a representation to separate addition and multiplication operations. So multiplications only happen in this layer. Now, of course, we can't just take any such network and implement matrix multiplication. So clearly, the naive matrix multiplication takes here the product of the dimensions of the matrices multiplications. So basically, if we choose this width of this layer wide enough, I think it's fairly intuitive that we can implement an exact matrix multiplication using such a network. In this case, basically these weights just pick the right entries and put them basically together into a multiplier. Now, I mentioned Strasson's algorithm before. It can also be represented as such a network. Now, in a 2x2 case, as you know, the Strasson's algorithm uses 7 instead of 8 multiplications, so we can gain something over this lower bound, although not very much. And yeah, to really have an impact, we would like to do much better. Now, in order to do so, we can relax some assumptions. For example, we can require this matrix multiplication only to be approximate, not exact. And then also, if you think about a neural network at inference, the weights are fixed, and the activations maybe follow some low-dimensional distribution. So in this case, we can we hope that we can, if one of the matrices is fixed and the other one has a specific distribution, we hope that we can go far below this naive lower bound. And that's actually the underlying idea. So we associate A with the weights or filters of our neural network, and B with the corresponding activations, and then learn these weights of the sum product network end to end for every layer, right? So basically we use a customized fast matrix multiplication for every layer. And hopefully, or as you will see in experiments, this allows us to go to basically choose this width here a lot smaller than what would be required in the naive case. Now, since at inference, so suppose we have learned these some product networks and we have this weight matrix fixed, since at inference we don't need to compute this branch of the network every time, so you can just collapse it and we end up just with a scalar, so we can just like simplify the network. Now, okay, so how do we do convolution? Of course, we can just write the convolution as a matrix multiplication and just like use this structure to compress convolution in the same way as just a matrix multiplication or matrix vector multiplication. But this is very inefficient because if you think about dimensions of current neural network filters and you think about vectorizing them, and so this becomes very high dimensional, and also by doing this we ignore the weight sharing strategy of the convolution. So what can we do instead? We can just basically compress or apply these sum product networks to subsets of the 2D convolution. Specifically, we can look at P by P output patches, and we can also compress the operation across the channels. So this is visualized here. So basically, we compress the computation of P by C out activation elements, and we do so by applying a strided ternary convolution here, which corresponds to WB, or one of the matrices of the sum product network. Then in this hidden representation that we get from this operation, we have a broadcasted multiplication. So we multiply each of these channels with a scalar, this A tilde, which is this WA times A, and then we use a transposed ternary convolution to basically transform the representation back up to the desired output dimensions. So yeah, so that's basically how we can adapt these networks to the weight sharing structure of the convolution. So yeah, so these are the dimensions. This here, this operation here is realized with additions and subtractions. Here we have multiplication, and then again additions and subtractions to go here. Yeah, we also have pseudocode in our paper. So if you didn't completely understand this here, I think it should be fairly easy to understand if you look at pseudocode. Yeah, and this gives us a pretty drastic reduction in the number of multiplications. So if you plug in numbers of common neural networks architectures here, so number of input channels, number of output channels, filter size, and patch size. So this can be pretty large if you choose R on the order of the channel dimension. Okay, so that's basically the idea, but we also have to learn these ternary weights, right? They're discrete, and quantization is not differentiable. So yeah, but we want to keep it simple and use standard techniques. So there in recent years, a couple of very simple methods have been developed to train quantized or train neural networks with quantized weights, and that's what we do too. So we maintain full precision weights, full precision version of these weight matrices, WA, WB, and WC. We quantize in the forward pass, ignore quantization in the backward pass, and update the full precision weights. I think this is fairly well known. Then we use a couple of other tricks. So we noticed that it is helpful to train these some product networks with full precision first and activate quantization later. And finally, we can also use knowledge distillation as proposed by Hinton et al. In 2015. So we just add a regularizer, cross-entropy regularizer of a teacher network, and the student network, which is the one we apply our approach to. And yeah, of course, we use just normal SGD, or you can also use Adam. Okay, so now we tested this on different applications, namely on image classification and language modeling. So let's have a look at image classification first. So we look at this ResNet 18 model that has been used by multiple other works, and we apply our method to every layer. So in this plot, you can see some baselines. So FP here is the full precision model. It has a top 1 accuracy of a little below 70%. Then here, these TTQ, BWN, and TWN, these are all binary networks that do binary and ternary quantization, and therefore also reduce the number of multiplications quite a bit. The pluses are ABCNet. This was proposed in NIPS last year. They do a little bit of more sophisticated approach. And yeah, we look at the multiplication. This was our goal. But we also look at the additions, and we look at the model size. So here, these colored curves are different variants of our approach. So the marker types correspond to the width or the number of multiplications normalized by the number of output channels. And yeah, we do this spatial compression where we also compress output patches. And then what I didn't mention before, but we can also do is you can implement these ternary convolutions as grouped convolutions, which reduces the number of addition. So if you want to control that parameter as well, you can do it there. And you can see, so yeah, depending on which configuration you use, you get more or less multiplication reduction. But in any case, for a given target accuracy, we basically, or the blue, so if you do spatial compression, we basically get we use fewer multiplications than our competitors, and in certain cases also fewer additions, or in this case then ABCNet. And we also get some small model size reductions, but they are not as significant as maybe other approaches that focus on model compression specifically. So this is all without knowledge distillation. Now, if we use knowledge distillation, we can get significantly better. And the field markers are with knowledge distillation, and basically what you can see here, we really can match or almost match the accuracy of the full precision model at a reduction of over 200x. So yeah, we think that is pretty significant. And here, if you look at the increase in addition, it's almost it's really small, right? It's not even 2x increase in addition. Yeah, so the second applications, as I mentioned, is language modeling, and we evaluated on Penn Tree Bank. We used a compact network that consists of convolutional layers, highway layers, and LSTM layers, and we applied our methods to all of these, so also to the LSTM layers, which are maybe more susceptible to quantization or to compression because you can have error accumulation. And this is what we got. So here you see the perplexity as a function of multiplications, additions, and model size. So the dotted line is with knowledge distillation, the other one is just without knowledge distillation. And here, as we increase the number of multiplications, you can see that the perplexity is quickly reduced. Without knowledge distillation, you don't quite match the performance of the full precision model here. But with knowledge distillation, we can again significantly improve the performance, and again we get a reduction in the number of multiplications on the order of 2 to 300x. Now finally, I would like to share another experiment. Here we try to learn exact matrix multiplication, so for 2 by 2 matrices, very small ones, and the idea was to see whether our algorithm can actually recover Strassen's algorithm, and the answer is yes. So we get a set of weights here. Yeah, this doesn't tell much, but you can basically use them to get a matrix multiplication of 2 by 2 matrices with 7 multiplications. And the weights are different from those proposed by, in the original paper. And yeah, if you think about it, the solution space is pretty large. Okay, so to conclude, yeah, we proposed and evaluated a versatile framework to learn fast approximate matrix multiplications for neural networks end to end. We got significant reductions of over 99.5%. While maintaining the accuracy of the full precision model in 2 different applications. And we also showed that our method can recover exact, so a fast algorithm for exact 2 by 2 matrix multiplication. Now, I just showed how to apply this method to just fully connected layers basically and convolutions, but we can also apply to other types of operations like group equivariant convolutions and deformable convolutions. In principle, we haven't done this, but it would be interesting to do it actually and see how it performs. Then, yeah, what I showed are arithmetic gains, right? And there is a considerable effort involved in putting this actually on hardware, but it would be really interesting to see how large the performance gains or energy gains actually are. And also the last experiment I showed seems to be encouraging to see whether this approach can be used to learn more fast exact transforms. Okay, that's it. We also have code, so you can play around or check our poster number 99 tonight.
Any questions? I have a quick question.
Yeah.
So how difficult is this to train?
So actually it's not very difficult, right? So you can really basically pre-train with full precision weights, and then you activate quantization, and then it continues. And yeah, you basically get very quickly when you activate quantization, you get you get to a plateau. But obviously we get some gains from distillation. This means that there are some optimization difficulties, but yeah.
So training time is about the same.
Training time is a little longer because you implement everything with full precision, right?
Right.
So you have, yeah, 2 convolutions instead of 1. Thanks.
All right, let's thank our speaker one more time. All right, so we appear to be missing our third speaker. If you're in the audience, you should come up. So we were going to go ahead and go to the final speaker in the session. You want to go? Change of plans. All right, so we do have our third speaker. So our third speaker should be Junwoo Woo, who will be speaking about deep k-means, retraining, and parameter sharing with harder cluster assignments for compressing deep convolutions.
Sorry, it just... hello everyone, I'm Junwoo Woo. Today I'm going to present deep k-means, retraining and parameter sharing with harder cluster assignment for compressing deep convolutions. This is a joint work done by Texas A&M University and Rice University. Sorry. First I'm going to go through the motivation, then our proposed cluster-inspired compression method, deep k-means, and then our newly proposed energy-aware matrix, and finally our future works. Sorry, it's a little bit it's weird. So the motivation here, there's been a growing trend in deploying CNN onto resource-constrained platforms. So those devices are usually have not very much memory and not very much battery life. So the 2 important concerns here is the model size and energy efficiency. A paper recently proposed by MIT said that these 2 concerns are often not aligned. So basically, lower model size doesn't mean you consume lower energy. So in our implementation, we consider both. So our proposed approach is based on parameter sharing via row-wise k-means. So here's an illustration of our methods. So basically, as we know, there's usually many repeating patterns in the filters of the convolution layer. So we assume that if we cluster those filters into K clusters, there shouldn't be very much performance drop. So what we do here is, given a certain convolution layer, we first concatenate M filters, as shown here, into a large tensor, and then we take each row out to form a long matrix W, where the shorter dimension of the matrix is S. S is the filter size. And after that, after we get the long matrix W, as shown here, we actually apply k-means on that filters W, so that we cluster those n samples into k clusters. Finally, we put each row back to their original position in the filters. And so, because, oh, that's weird. Sorry. So, because we already do the clustering stuff, so so after the compression, we only need to encode k cluster centroid and its corresponding weight assignment index. Here's a calculation of what's the memory consumption after the compression. Oh shit! Sorry. That it seemed like it's just flip automatically. No, that should be fine. Just sometimes. Much better. Oh, I'm sorry. I'm sorry about that. Yeah, so here is a filter visualization of a convolution filters in wide ResNet before and after deep k-means. So basically we can see there's actually more repeating patterns on the right side because we do the clustering. But there is not necessary to be repeating the same filters because we do the clustering in a row-wise fashion. So there should be the same rows across filters. Here's a quantitative result here. But surprisingly, we found that if we use deep k-means directly, there is actually considerable performance drop. For wide ResNet, we drop considerably, and also for the Google Net. And so we're thinking that if that is possible to design a retraining process that is more suitable for k-means. So we came up with a k-means regularizer, which actually the aim of the regularizer is to make the weights more suitable for k-means, so that there won't be very much performance drops after we employ the deep k-means clustering method. So our proposed regularizer is actually inspired by the spectral relaxation method proposed in NIPS 2001. And so first, the original k-means objective can be written in bulletin 1, where F is the index matrix with a spectral structure, where each row represents the membership of the samples. Then in the bulletin 2, we can further rewrite the equation into that shown in bulletin 2 because W is given, so we remove the first part. And finally, we relax the objective to the equation in bulletin 3, which the spatial structure of membership matrix is relaxed into a orthogonal matrix that is F transpose F equals to identity. Note that W is no longer a variable during training, so we need to update F and W alternatively, where W can be updated by a SGD, and F actually is updated by a famous Chi-Fan theorem. Here's our final formulation of the objective function. Note that we multiplied the regularizer by a factor lambda. Here's another realization of the filters after we employed the retraining scheme. So as you can see, the middle and the right one looks very the same. This is actually what we want because we want the filter pattern before and after k-means to be similar so that there won't be performance drop here. Actually, you can see the performance on the right one is actually a little bit better than the middle one, probably because the regulation effect. So here's our result. After retraining, you can see that, so DK means WR is without retraining and DK means is with retraining. We can see we actually beat the state-of-the-art software sharing method and on WideResNet, and also we are better than Oneshot method and low rank in Google LENet. So here's a little bit more experiment. We tried other networks such as FreshNet proposed by Chen and TTCom proposed by Granblue, and we also have result on Cafe on LENet 5 Cafe, which is shown on the right side. So another thing I want to say is, so we further propose a energy-aware matrix which aim to predict the runtime energy cost. We divided the energy-aware matrix to computational cost and weight activation cost. So the computation cost is aimed to measure the computation resources need to generate a single decision, basically a 1 4-bit adder. The weight activation representation cost is to measure the storage complexity and communication cost associated with data movement. So basically, the energy cost is made up of both computation and data movement. Basically the excess of DRAM. And so we verify our matrix with a energy-aware matrix proposed by MIT, and where their method is actually extrapolated from actual hardware measurement. I'm sorry. So I'm gonna go quick. So here's a result of our energy-aware matrix. So we perform better than state-of-the-art filter pruning method, CAR. And so our future work will be we would like to integrate deep k-means into CVDN to get real energy performance, and we also want to exploit more adaptive K selections. And also deep k-means could be applied with other compression methods such as pruning or structure filters. And also deep k-means is currently not directly optimized towards energy-aware goal, so we aim to maybe design an energy-aware loss function. Yes, that's all. So we have the code available here, and our poster session is at 1:04. Thank you.
All right, so since we're running a little bit behind, we're going to hold off on questions and go to the poster for that instead.
Yeah, fine.
All right, so this is the final speaker for the final session of ICML. So this is going to be Tommaso Forlanello, who's going to talk about born-again neural networks.
Hi, everybody. So I will be also finally fast. The idea is that, so this is a joint project between, that started during my internship at AWS with Anima and my lab, my advisor's lab, iLab at USC. So the basic idea is that we found this interesting empirical result that knowledge distillation between identical networks, so when a teacher network teach to a student network with the same parameterization but a different random seed, we find that at least in a lot of settings that the student systematically improves with respect to the teacher. And in the situation where it doesn't improve, it's always like in quite corner cases. Furthermore, we find that ensembling these multiple generation of models lead to stronger ensemble than the independent ensemble. So why the title Born Again? Because of a really late paper from Leo Breeman, where he's basically showing the first empirical application of knowledge distillation, compressing ensemble of forest of trees into a single tree so that they could be easily deployed with the 1990s technology. And then you might see some commonalities in how much we end wave. So the general interpretation of knowledge distillation is given by Hinton is that there is a dark knowledge hidden in the wrong outputs of the teacher, so not in the non-correct outputs, and this dark knowledge conveys similarities, information on the similarity between the classes, and then this can be helpful to the model. They use it mostly for compression, as we have seen, but also Michael presented the results where also during compression you can improve the performance of the student, even if compressed. In this case, we're not going to be using compressed model. So normally, this is what happens when you are using one hot label with multi-outputs. They are going to have the only contribution to the gradient is going to be given is going to be in the correct output, where you have a probability of 1 with respect to the one hot label, and then the difference between the model output and the ground truth output is going to define the scale of the gradient that is going to get back propagated. In the knowledge distillation case, as you can see, the main category, the correct category, is not contributing so hardly to the gradient, and there is an additional contribution given by the output of the other categories. We mostly train our models experiment on a dense network. Why do we do that? Because we want to work near state of the art, and then we reach, but we actually improve with respect to the previous performance of dense nets, because we think that finding improvements on models that are far away from the best performance is really easy, and then it's really easy for other people to disprove it. So the main idea here is that we take multiple dense net. I spent a lot of graduate student descent on optimizing these models over CFR 100 to get them at the level of the original published paper and to improve a bit with respect to that. You can see that there is a sequence of model going from really deep and thin model to quite deep and really wide models. The idea is that there is a scale of around the bigger model than SNET 18120 is going to be around 10 times more heavy in terms of parameter, and on the order of 50 times more costly in terms of memory use on the GPU. At the beginning, the performance difference between these models is around 1.5%. So the teacher column is indicating the performance of the best performance that we can get with the HGD with momentum. And then band 1, band 2, band 3 are the consecutive generation of students trained from the model on their left. And we can see that, especially for the smaller model, there is a multiple generation keep improving. And we find at the end that the best model at the last generation of the smallest configuration ends up performing better than the biggest model I originally see, which gives a compression rate of about 100%. Like it ends up being like 95% less parameter for the same result. So here we have some other results with this is all done without using any label. So ban plus L is a situation where we are also using the original labels, and we find a distortion with respect to we find improvement in the performance, but we find quite a distortion. But this is mostly due to the fact that the teacher on CIFAR 100 training set has almost 100% accuracy. So not using the actual label, but using the teacher, it doesn't give any difference. We will see another experiment that when our teacher is not fully overfitting, or better, is not fully fitting the training set, then we require also information from the original label. Ensemble 2 and 3 shows the effect of ensembling the model, and the first configuration is a comparison of a submitted paper at last I clear, where they were getting around 1% higher error for the same configuration for ensemble 2 and 3. So the bottom column, the bottom table instead is showing different configuration of students taught by the teacher 9060, where we maintain the size of the hidden states constant, but we change the number of layers in between the representation, or we try to, where we change multiple parameters, and we find that mostly unless we drastically reduce the number of parameters in DenseNet, we are able to maintain the same performance. So there is also furthermore compression that can be done by changing the architecture in smarter ways. And then, of course, after this, stuff like StraussNet can be applied really efficiently. Same result on CIFAR 10. Here we show that, which is a data set that is quite saturated. We find that smaller models that are not near state of the art easily improve, while bigger models that are pretty much the best model that you can get are not improving, and maybe it's a healthy thing that we don't get to 99% accuracy. So then the idea is, like, why is this happening? And is this because of dark knowledge with the same intuition given by Hinton, or is there something else? The idea here is trying to identify whether the contribution to this improved performance comes from the fact that the teacher is reducing the size of the gradient with respect to the correct class, or because of the introduction of the additional gradients from the wrong classes. So this is the first treatment that we use, which we call dark knowledge with permuted prediction, which is exactly the same as dark knowledge, but the wrong outputs are permuted. This way, the second order, high order information between the outputs are maintained, but the exact attribution of the actual class is mistaken. The second treatment that we do is we interpret the downscaling of the correct choice by the teacher as an importance weighting of sample. So we actually use the original label, but do importance weighting of samples based on the confidence of the teacher, interpreting confidence of the teacher as the score in the argmax of the teacher. These are the results in terms of accuracy for the smaller and the biggest model, and in blue is the original performance of the teacher. In red is our best performance, that is the complete knowledge distillation loss. And orange and green are respectively the two treatments. And as you can see, there is except for the biggest network, there is an improvement from both. So we think that there is a joint work between the effect on the main and on the correct output and the wrong outputs. Actually, the main motivation for this approach was to train DenseNet to do knowledge distillation between ResNets and DenseNet, between DenseNet and ResNet, and then further compress ResNet, because ResNet are much better to utilize for deployment and for inference. So we systematically find that using a ResNet student with a DenseNet teacher, we can even improve with respect to the original DenseNet accuracies. Tendentially, we require to have we do it by maintaining the size of the hidden states every time there is a spatial contraction in the DenseNet or the ResNet equivalent. And also, together with Michael, results that you have partially seen in 2 talks ago, if we apply knowledge distillation to sequence-to-sequence model for language models, we have the same effect of reduction of the perplexity over both validation and test set, in this case for Pentry Bank. Analogously, if we have instead a ResNet teacher with we use a DenseNet student, we find that for a reasonable model like WideResNet 28.5 or WideResNet 28.10 that have training accuracy, test accuracy that much lower than the original DenseNet, we are anyway able to get DenseNet students that are better than a DenseNet trained with the original data, with the original labels. So this is a lot of literature that is related. I received quite an interesting amount of emails of people showing like one small result in their paper where this was happening. And some of these papers are actually set papers that inspire me, where I thought that this could happen in their setting. An interesting paper here is that is kickstarting deep reinforcement learning. Thankfully replies to one of the reviewers that asked whether this would work or not in deep reinforcement learning, and thankfully DeepMind spent the money for us on demonstrating it. Finally, of course, everybody wants to claim ideas, but if you go back to the Bible, you will find chapter 17, where Minsky speaks about sequences of teaching selves, and where pretty much the architecture structure come on. The original drawing is just a printable version of this. Then to thank Zach, Mikael, Anima, and Laurent for all the work, and also Pratik, Kamyar, Sebastian that helped in a lot of conversation, and Rich and Sami Banjo that I bored to death conversating about this stuff at the NIPS workshop on meta learning.
Are there any questions? All right, since it's the end of the day, let's conclude this session. I'd like to try to thank our speakers one more time, all of our speakers. Thank you.